Good morning, everyone. My name is Brian Camey with Risk Management Professionals, and today I will be going over the independent protection layers, also known as IPLs, that are utilized within your layer of protection LOPA analysis. So let's go ahead and get started. This slide is just a brief summary of all of RMP's services. So our core competencies and expertise reside in EPA RMP, OSHA PSM, CalARP. We also specialize in HAZOP and LOPA studies and other hazard identification techniques and a variety of other process safety and regulatory standards. So today I will be going over a brief overview of what LOPA is to help familiarize ourselves with the concept. I will give an overview of what an IPL is. I will talk about the specific core attributes and characteristics. And finally, I'll summarize everything that we talk about today. Let's begin with what LOPA really is. The traditional methodology utilized during a process hazard analysis, also known as a PHA, is the HAZOP and LOPA approach. So as you see from this image, in the very center, we have kind of a middle effort that is utilized. Moving towards the right, you see a higher amount of effort that has to go into these forms of analysis. To the left, you have less effort, like a checklist. HAZOP's right down the middle. It is a qualitative approach, while transitioning into LOPA, that's where it is a more quantitative approach that is backed by the CCPS guidelines, developed using a little bit more of a statistical approach. So more on the numbers game compared to a how you feel approach in a HAZOP. The overall risk is calculated and determined based off of frequency and severity. So the goal of a PHA, as we all know, is to identify a cause. We then want to determine the most probable worst case consequence and overall severity, whether that's safety, whether that's environmental, whether that's some type of financial. That then will be analyzed following a review of the applicable safeguards utilized for a scenario, whether that's procedures, whether that's an alarm, some type of automated trip. The evaluation for this frequency is then based off of experience, which will determine the final overall risk. So what is the probability of a valve to fail, considering a worst case consequence, assuming that all of our safeguards in place are working, based off of experience, what do we think that overall frequency will be? And that is normally how we determine the frequency and overall risk during a HAZOP. Once you transition into a LOPA, that is utilized for our high severity scenarios. So, transitioning from a first aid injury all the way up to a potential fatality, that is what we focus on in the LOPA approach. So this method allows for the frequency to be determined through statistics rather than a qualitative experience-based approach. So what does this rely on? It relies on the likelihood and probabilities using standardized values from the CCPS. As a result of this, it often leads to greater frequencies and a risk ranking that can help you really identify gaps in your design that you may overlook in a HAZOP by not looking at this quantitative approach, and this could result in the need to consider additional safeguards or any type of recommended actions that may normally not be caught during a HAZOP. Now let's go into more detail about what an IPL, or the independent protection layer, really is. Protection layers are utilized to either provide preventative or mitigative support for a hazardous event. Independent protection layers could be a device, a system, or some type of action that is capable of preventing a scenario from proceeding to an undesired consequence, regardless of the initiating event or the action of any other protection layer associated with the scenario. So something that's important to note here is the independent portion of this, right? If a transmitter is shared for a trip and alarm, only one of those would be credited as an independent protection layer as they are feeding off of the same transmitter. So that's something to note when we're going over these characteristics. So the image on the right highlights the different examples of protection layers. These protection layers are divided into two major categories, one being prevention, the other being mitigation. So for our preventative protection layers, they will stop this scenario completely, or they will prevent an undesired consequence from developing. So some examples of these are to rely on the process design to limit the scenario from achieving an unsafe state. So that could be the actual allowable design pressure or the design temperature of your piece of equipment or piece of piping. If that is designed adequately, then that can completely prevent a consequence from developing. You could also consider process control, such as some type of control loop that's utilized to modulate some process variable to achieve this safe state. If these happen to be exceeded, you can still rely upon an alarm with some type of operator intervention that can be utilized to allow for the ability to correct the process prior to you reaching that next step, being a trip, right? So if you have an alarm point, you have an operator response associated with that an operator will receive, it gives them the time of day to review the scenario, diagnose the situation, and provide some type of corrective action to help prevent the scenario from developing further or getting into a hazardous state, to allow for the trip to not be triggered, thus potentially shutting down your system, having a financial impact, so preventing from that next step. Without any of these preventative protection layers, the system may be reliant on the upper half of this chart being mitigation. So for these mitigative protection layers, they are utilized to prevent the consequence from developing further once it's already occurred. And it's also to help produce a less severe consequence from occurring. So some examples of these begin with an active form of protection, such as maybe a relief valve. You're building pressure in your vessel. It gets to the set point of the pressure relief device, which then lifts to help prevent the scenario from developing further. As you move up this chart, you then could potentially have some type of loss in containment. If you do get this loss of containment, an adequately sized passive protection, such as a dike, could be utilized to help limit the spread of personal exposure. And finally, as a last resort, that would result in the least robust protection layer, would be to rely upon some type of emergency response. Once the hazardous event has already developed, there's no way for you to prevent it. It's just a means of you limiting the spread of this event once it has already occurred. Although all IPLs are derived from safeguards, there are some safeguards that are not considered IPLs. The most common of these being training, certification, or some type of reliance upon standard operating procedures. They can be used throughout the HAZOP, but not included as a LOPA IPL. Additionally, non-IPL safeguards could include some type of testing, some type of inspection, some type of maintenance. You may have some type of communications or signage around hazardous materials. And finally, if you do get to the point of a release, any type of fire protection is traditionally not captured or recognized as an IPL. Now let's get into the core attributes that are associated with what we consider an IPL. The attributes that should be considered when identifying IPLs is important to the overall concept of what it means to be an IPL. It is important to have a detailed understanding of the independence, the functionality, your overall integrity, your reliability, your auditability, your access security, and your management of change requirements for IPL credibility. I will go over each one in detail over the next few slides. To credit a safeguard as an IPL, it is important for it to be independent from the initiating event and from other safeguards or IPLs that are being credited for a given scenario. So one of the most common examples of this is shown in the image on the right, describing the independence from the initiating event. If the scenario that we're looking at or considering is LV1, the control valve malfunctioning open due to some type of misreading from our level transmitter 1, the existing high-level alarm that is associated with the overall control loop may not be credited, as it may not be independent of the initiating event. So this could cause some type of inability for the alarm to come into play. So traditionally we would see this as not being independent and not credited as an IPL for this specific scenario. Another common example is common mode failure that may be due to two transmitters on the same tap. That can be challenged for this type of common mode failure. So an example here is one of these taps is utilized for an alarm. The one on the bottom of this tap, the one above, is tied to some type of safety instrumented function. So because these transmitters are very close in proximity, they can give you a misreading and ultimately lower the ability for you to have a credible IPL in this event. So that's something else that's important to note when considering independence for your IPLs. Functionality is another key importance when analyzing a safeguard as an IPL. It must function to either prevent or to mitigate the consequence of the scenario. So for a scenario that is relying on a PSV, as an example, to provide relief, it is important to perform the relief valve design basis calculations for specific scenarios to ensure that the capacity of the relief device is greater than the required relief rate calculated. If this is overlooked, this may lead to some type of future gap in the design that can lead to costly impacts to personnel as a result of an undersized PSV. So just assuming that a PSV is sized for a scenario is not adequate. If we are crediting this as an IPL, it is very important for us to verify in our documentation that the existing PSV is adequate. When an initiating event occurs, the process conditions may change from normal to abnormal, and thus the IPL response needs to be timely. So the first of these times that we'd like to consider when looking at our IPLs is the process safety time. This is the time between a failure occurring in the process or its controlled system and the occurrence of the hazardous event. The IPL considered during the scenario would need to interfere within this timeline in order for it to be adequately credited. So an example of this could be during a liquid overfill case, where the process safety time would be the time that it takes for some type of vapor space of a vessel to fill and the pressure to then build, creating some type of overpressure within the vessel and have a potential release and a personnel exposure. So that process safety time would be the amount of time for liquid to increase and overfill your designated vessel, causing this safety concern. The next time that you'd like to consider is the IPL response time. So that is the time for a given IPL to detect an out-of-limit condition and to complete the actions intended to achieve a safe state. So the key words to note here are detect and complete the actions associated with the IPL. Once the response time is considered, the end of this time is when the process lag time begins. So this is the time it takes for the process to achieve or maintain its safe state. And this is an important timeline to consider when developing your overall set point for the IPL, because we want to make sure that we allow for adequate amount of time for your operator response to act prior to that hazardous event developing. The set point can also be referred to as a maximum set point, which would allow for a sufficient time for this diagnosis and the corrective action from your operations folks. Considering the response time and process lag time will help ensure that these times are less than the overall process safety time to provide a credible functionality from your overall determined IPL. So that's the big ticket item here. We want to make sure that the combination of those two times is still less than process safety time so that we allow for this IPL to be credible in whatever scenario that we are mentioning. Dependability is also an important quality to consider for an IPL because it must be available to provide its intended protection when needed. So one way that we like to ensure this is that it's important to include quality data that is backed by recommended manufacturer maintenance or operating procedures. This includes the need for operating procedures to be up to date and operations and maintenance to be adequately trained for these practices. Finally, thorough and organized inspection, testing, and preventative maintenance records are also important as part of any type of SIL verification, which we'll get into some more details in the next slide. SIL verification is one aspect of IPL development that is important for the overall risk reduction factor associated with an IPL. So the risk reduction factor is how your overall risk gets reduced based off of the reliability of your IPL. So for a greater SIL rating, measuring its reliability and giving you a greater RRF value, thus reducing the risk as your SIL rating goes up. SIL 0 ratings are traditionally associated with interlocks or alarms. They're not rated, nor do they require any more than one layer of protection, so these are our simplest systems. Moving up to SIL 1, this does require a calculated reliability score with at least one layer of protection. This requires regular proof testing for this calculated value, which essentially means that you are maintaining this SIL rating. If you are determining an IPL as a SIL 0 through 3, specifically 1 through 3, which require calculations. These must be regularly proven to still be adequate to ensure that you're maintaining that value. So if we're crediting it during the LOPA, it's important to note that these values need to have documentation associated with them. So moving into a SIL 2, this requires a calculated reliability score up to a 99 to 99.9% value, traditionally with at least 2 layers of protection. These systems require regular proof testing and require some type of redundancy. An example of this could be some type of 2 out of 2 logic where there's multiple transmitters that have to get to your set point in order to activate this safety instrumented system. And finally, talking about SIL 3 ratings, they're generally avoided. This is because of its heavy testing and record-keeping requirements needed to maintain this rating. It requires at least 3 layers of protection and has the highest risk reduction factor. So that's why the maintenance, testing, and inspection practices that go into our IPLs are heavily correlated to the presented SIL ratings that we've shown here. And that's why this should help capture the importance of how your dependence heavily affects your IPL and its credit when considered during your LOPA. Another important aspect of an IPL is its reliability. To be considered reliable, it must be operating as intended in the operating environment for an expected time. So the image shown of the detonation arrestor is shown as it's designed for a specific process environment and is subjected to rigorous testing based on the defined protocols and specs to assure reliability. Auditability is another important attribute when considering IPLs. So this could include the ability of an organization to inspect procedures, records, previous validation assessments, and other documented information to ensure that design, testing, maintenance, and operation continue to conform to whatever expectations are established at your facility. To ensure this, it is important that there exists a means to audit performance of a management system related to your IPLs. It is imperative to the success of an IPL that the maintenance system, procedures, operator training are all regularly inspected to maintain proof of risk reduction and credibility of your IPL. So if this is not properly audited, practices may be assumed to be followed, and you may have personnel that may not be properly trained. That would reduce the reliability of your IPL, and you have this false sense of security that your IPL is more robust than it truly is, and that you're crediting this LOPA, reducing the overall risk when it's inaccurate to what is existing in your field and in your documentation system. The management of change process is a set of best practices used when a company makes a change that could expose or maybe create new hazards. So this process allows for personnel to review all aspects of the program and see how these items are affected. So traditionally, this process includes the need for reviewing any affected process safety information. This is for all personnel being affected by this change to be adequately trained. All operating procedures, operator actions need to be corrected, and to ensure that any action items that are developed throughout this management of change process are properly closed out and heavily documented to ensure that whatever file path is associated with this can be easily followed in the event of operations looking for more detail on what went into this change. So the auditing process established can help ask the questions if these items are properly being looked at following the management of change that could impact any of your IPLs specifically. So as an example, an alarm that's credited as an IPL may rely heavily on your operator intervention with a described operator response prompt that they do see at the board. So if this operator response is changed and personnel is not properly trained on this change, this could result in the IPL no longer being credible, as the response may not be adequate in preventing the consequence from developing. Access security is the final attribute to note that includes the use of physical and/or administrative controls to reduce the chances of unauthorized system changes, which may impair a safety device. So some examples of this could be car seals or locks on valves. Specifically, the requirement for block valves in a relief path for a PSV to be car sealed open to allow for adequate relief protection. In the event that somebody were to close one of these valves, the PSV being credited as potentially a main IPL for a LOPA scenario would be compromised and thus result in an unmitigated consequence to develop. Now let's summarize what I went over today. To summarize, LOPA is a quantitative approach that can be utilized to further investigate the likelihood of a high severity scenario to develop. If utilizing this methodology, should ensure that any protection layers considered have had their attributes reviewed to ensure credibility as an IPL. When reviewing these items, the most imperative items to remember are to heavily rely on your documentation and to keep organized records of all of your testing, your inspections, and clear maintenance practices to ensure that the overall quality and expectations that you've established for your IPLs are maintained throughout the lifetime of these IPLs. Thank you very much for listening. Are there any questions?